In this video, I'll talk about the Heaviside step function and its Laplace transform. So let's look at what is the Heaviside step function. So if this is t, x versus t, we can draw a picture of the step function starting at t equals 0. It's 0 over initial range, then comes up, and then is equal to 1. So the height here is 1, and the point at which the function is discontinuous we can call c. And then we define x. We define this function as the Heaviside step function, which we denote as u sub c. C is the parameter, which is a function of time. Okay? So this is the definition of the Heaviside step function. We can also call this a step up function because it steps up. So the formal definition of the step function will be uc of t is equal to 0 when t is smaller than c, and it's equal to 1 when t is greater than c. And where it changes, whether it's equal to 1 at t equals c or equal to 0 at t equals c, doesn't really matter, but we'll choose the definition where it's 1 at t equals c. Okay, so that's the step up function. We can also have a step down function. So the picture of the step down function will look like a function which is 1 and then steps down to 0. So 1 and then steps down to 0. Okay, so this is again occurring at c, and this is 1. And here, this function then is something that is 1 when t is less than c, and then becomes 0 when t is greater than c. So uc is 0 when less than c and 1, so we can see that this is 1 minus the Heaviside step function, right? And then this is the step down function. Okay, so now we have a step up function and we have a step down function. We can do one more function which is useful for modeling. That will be the step up, step down function. So we start down, we step up, we step down. So this will be the step up, step down function. Okay? Again, we step up to a value of 1. If we wanted to change that 1, we could always multiply by a constant. Now we have two parameters rather than just c, so we can step up, say, at a and step down at b. And how do we write the step up, step down function in terms of the Heaviside step function, which is the step up function? Well, we are 0 for t less than a, and then we step up, become 1 for t greater than a. So we have a u sub a of t, which is 0 for t less than a and 1 for t greater than a. And then we step down again at t equals b. So we can subtract from this something which jumps up to 1 at t equals b is 0 for less than t equals b, and that would be ub of t. Okay, and that would be the step up, step down function. If t is less than a, we get 0 minus 0, which is 0. If t is between a and b, we get 1 minus 0, which is 1. And if t is greater than b, we get 1 minus 1, which is 0. Okay, so let's see what else we can do with these step functions. An interesting thing to do is represent a translation of a function. So we can have some function defined from t equals 0. So let me draw some arbitrary type of function. We can have something like, may look like a sine function perhaps. Okay. And this can be our x equals f of t. And then we can translate this function a distance c. So let me draw that. So we can have a translation of this function. So rather than the function starting at t equals 0, it can start somewhere else here, and then it will be the same function, right? So moved. And then between 0 and this new starting point, we can put it equal to 0, right? Okay. So this value here then is c. And this is x equals g of t now. So what is the relationship between g of t and f of t? Well, g of t is 0 now for t less than c. So we have our Heaviside step function, which is 0 for t less than c, 1 for t greater than c. And then it's exactly the same function as f, except that when t is equal to c here, f is equal to 0. So it should be f of t minus c. Okay? And that corresponds to a translation of a function by c, where everything before the translation we set to 0. Okay. So we can look now at Laplace transforms. Okay. So let's look at the Laplace transforms. So the Laplace transform of the Heaviside step function, so the Laplace transform of u sub c of t, right? From the definition of the Heaviside of the Laplace transform is the integral from 0 to infinity e to the minus st times the transform of uc of t dt. And then we can use the definition of the Heaviside step function. So it's 0 for t less than c, and is 1 for t greater than c. So here we're assuming c is positive. Okay, so if c is positive, So the contribution to the integral for t less than c will be 0. So we can start the integral at c. And then we have the exponential function. And then when t is greater than c, uc of t is 1. So that becomes 1 and dt. So the Heaviside step function allows us to reduce the integral. This is easy to do. This is minus 1 over s e to the minus st, evaluated between 0 and infinity. The upper limit goes to 0. The lower limit goes to minus 1 over s e to the 0, which is 1. Sorry, the lower limit here should be c, right? So I'm integrating from c to infinity. So the upper limit is 0, and then the lower limit goes to minus 1 over s, which is 1 over s times e to the minus sc, or I can write that as minus cs. And then that's the Fourier transform of the step function. Okay. We can also do the Fourier transform of the translated function. So that one is the Fourier transform of uc of t times some function of t minus c. So this is the function that's been translated at distance c, where from 0 to c we set the function equal to 0. So this is the integral from 0 to infinity of e to the minus st times uc of t times f of t minus c dt. Again, the step function is 0 for t less than c, so it goes from the integral from c to infinity, e to the minus st, f of t minus c dt. And we can change variables here to do this integral. We can let t prime equals t minus c, so dt prime equals dt. And we get the integral of substituting in t equals c. We have c minus c, so t prime goes from 0 to infinity. We have an e to the minus t. T is t prime plus c, or c plus t prime, times f of t minus c is f of t prime times dt, which is dt prime. And we can factor out e to the minus sc times the integral from 0 to infinity e to the minus st prime f of t prime dt prime. And this is just the Laplace transform of f of t, right? T prime is a dummy variable. So this is e to the minus sc times the Laplace transform of f of t. Okay? And those are two Laplace transforms that have use when solving inhomogeneous terms that are discontinuous.